All right. So at the Technion, I teach heat and power integration in a 3-week sequence, which focuses on heat exchanger network synthesis using pinch technology. I will now give you guys a 20-minute or so overview of materials covered in 5 to 6 hours of online lessons, 6 hours of class meetings with students, and 9 hours of active tutorials in which students solve problems for themselves. These materials are taken entirely from chapter 11 of the textbook. So let's just first an overview of what happens in those 3 weeks. All right. So in the first of the 3 weeks, it's an introduction to Henn synthesis. Students have to be aware of the significance of the pinch. They have to know how to do maximum energy recovery targeting. We teach both the composite curve and the TI method during the lectures, but I will only cover very briefly TI method in my presentation today. And in any case, it's the most efficient way to do this, but has less of a physical intuition. That's why we do both. And finally, they have to do basic Henn synthesis for very simple problems involving, let's say, 2 hot streams and 2 cold streams. That's what they would be doing in the first week. In the second week, we move to advanced Henn synthesis. So they have to learn about the idea of what is the minimum number of units that you can design for a heat exchanger network. And that brings naturally to the idea of heat loops and how to break them and the cost of breaking them. We teach how to stream split, how to make stream split design meet essentially both the MER target and the minimum number of unit target. And we cover threshold problems. And in the last of the 3 weeks, we bring everything to reality. That is, we connect to the real process. That involves teaching the students how to do data extraction from real flow sheets, mastering the usage of the grand composite curve, which enables marshalling alternative utility sources to minimize costs. And finally, rules about heat integration of reactors, distillation columns, heat engines, and heat pumps. Let's go into some more detail. So here is the first part, introduction. Here are the instructional objectives. As I said before, you are given data for hot and cold process streams. You should be able to compute the pinch temperatures, compute the MER targets, and design the Henn to meet the targets. Very, very straightforward, simple first week. We walk before we run. Typically, they'll get a problem to look at. This is a very simple example problem involving 2 units, 1 reactor, 1 column, 1 separating column, involves 4 possible streams for heat integration, 2 hot, 2 cold. So for each stream, you would have its source temperature. For example, for hot stream 1, source temperature is 180 degrees, target temperature 80 degrees. The enthalpy change is 100 kilowatt, which means the flowing heat capacity is 1 kilowatt per degree centigrade. The same method is used to extract data from the others. Of course, in reality, we would need to be doing this from real process streams, but that comes later. So the objective is to design an efficient network of heat exchangers, water coolers, and steam heaters to minimize the required external energy for the system, satisfying at the same time a minimum driving force of 10 degrees centigrade. The temperature interval method, which is what we teach, it involves 3 steps. First, we adjust the hot and cold stream temperatures to bring them to the same reference. Typically, what that means is we remove delta T min from all the hot stream temperatures. That means now we're only talking about 1 temperature scale, the cold stream scale. We then determine temperature intervals by just stacking the determined temperature intervals that have been extracted in a descending order, defining for each temperature interval the enthalpy balance, gives us the possibility to do calculation of the enthalpy cascade. Basically, we stack the intervals. Between each interval, we have the enthalpy change that we just computed. We assume no external hot stream required, and then just cascade down, estimate or compute the minimum residual enthalpy. And of course, this minimum residual enthalpy has to be 0 or greater. When it is equal to 0, we now have the MER target. So here we have 60 kilowatts of heating, 225 kilowatts of cooling as our target. And we've identified the pinch temperature of 140 degrees centigrade cold and, of course, 150 degrees centigrade hot. Very good. Why is the pinch significant? Because it defines the problem into two portions, a heat sink above the pinch and a heat source below the pinch. Above the pinch, we are only allowed to use external heating, and the targeting allows us to estimate the actual value. We just now calculated QH min. Below the pinch, there's a heat source, therefore we can only use cooling, and the minimum cooling requirement has just been determined by the temperature interval method. We then have to design a heat exchanger network that meets the targets. For, of course, the first step being targeting, which we just did. So, for example, for the problem that we started the section with, there's the reactor and the heat and the distillation column. The minimum heat requirement is 48 kilowatt. Minimum cooling requirement is 6 kilowatt. For delta T min of 10 degrees, the pinch temperatures are 70 hot, 60 cold. So the first thing we do is we take our streams, all four streams, separate the system at the pinch, and then design first above and then below the pinch. Two separate design problems. And what is really key, the students have to get this point across, that the design is always from the pinch moving outwards. The reason we do that is at the pinch, the system is most constrained. At that point, all the hot streams and cold streams at the pinch are exactly delta T min apart, and we have to make sure that we do not violate this limit. So there are rules. Immediately above the pinch, we pair such that the hot flowing stream capacity has to be less than or equal to the cold stream capacity, and tick off. The other important thing to notice is, since we start by designing above the pinch there is only hot utility allowed. Therefore, all the hot streams have to be cooled by cold streams. Therefore, the key is to eliminate the hot streams first. So, using this rule, we have to pick a cold stream to match the only hot stream at the pinch. In this case, would be H2. And we have to make sure that the cold stream flowing heat capacity is greater than the hot stream. Since the hot stream flowing heat capacity here is 2 kilowatts per degree centigrade, obviously we have to match it with C1. And we load this heat exchanger in such a way that we tick off one of the two streams. In this case, we have now eliminated H2 above the pinch. That cooling requirement has been totally satisfied by C1. We then have to decide what we do with H2, and obviously we're going to match this with the other cold stream that is still available, and load it in such a way that we tick off one of the two, whichever has the lowest heating or cooling requirement. We tick off H1. We've now eliminated both the hot streams, which means we now just basically add trim heaters to complete the design above the pinch, and simultaneously also match the hot target. The same rule in reverse is applied below the pinch. And that's basically what the students have done in the first week. That's their level. We then move in the second week to advanced Henn synthesis, basically how to identify loops, how to break them and at what cost, how to design split stream designs, and how to design threshold systems. That's what we're doing in the second week. So I'm not going to go into a lot of detail here. Basically, there is a way of estimating the minimum number of heat exchangers and thus determine how many loops there are in the system. In stream split designs, the idea is to, for example, in this case, where we have an example situation with one hot stream, two cold streams, the one possible solution would be, well, after we've done the calculations for targets, we see that MR targets require no external heating, no external cooling, and the unit target gives us a value of 2 units that we should be able to satisfy. A student who was totally asleep in the first week of the course might design something like this, which involves 4 units, 2 above the minimum, and also requires heating and cooling utilities, which are above the minimum values of 0. Anybody who does this was not around in the first week of the course, so hopefully no one will design this by the second week of the material. But somebody who doesn't know about stream splitting would do this design, which on the one hand manages to satisfy the MER targets, but unfortunately has 2 more heat exchangers than are required. Learning about stream splitting will allow us to do this for a design, that is to split the hot stream and maximize the driving force available between the two cold streams that need heating. And this actually is the stream split design. There are rules associated with the stream split design, the details of which I will not trouble you with in the interest of time. But what do we do with this? We now are able to deal with more complicated problems. The kind of problem that a student would be solving by the second week of this material would be this monster here, which after the initial heart attack that students will experience, they will soon realize that if they apply what they've learned, it's not as tough as it looks. All right. We start by targeting, right? That's what we said. So targeting means remove delta T min from all the hot streams, do interval balances, do the energy cascade, compute the targets. So here are our targets. We have 1,020 kilowatts of heating, external heating, 1,800 kilowatts of external cooling, and the pinch is at 190 degrees centigrade cold. Obviously, for delta T min of 10 would be 200 degrees centigrade hot. So now we're going to do the design first above the pinch. The only streams that are actually active above the pinch, 200, 190, as you see here, are H1, H2, C2, and C3. And actually, this is very, very easily solved. This is actually the easy part of the problem. And here we have a solution which actually manages to satisfy the minimum number of units. And of course, we managed to satisfy also the energy target of 1,020. However, below the pinch, the situation is somewhat more complicated. Again, in the interest of time, I will zip through this solution, but trust me, this is what we do in class with the students, and they help me solve this problem. The trick here is to realize that we have 4 hot streams and 2 cold streams at the pinch, right? So we have to deal with C2, C3 first of all. One possibility is this. Here we've killed C2, we've satisfied C2, which is wonderful. Now we have C3 with a flowing heat capacity of 22, which we cannot match directly with any of the hot streams, because below the pinch, we need to ensure that the flowing heat capacity of the hot stream matched at the pinch has to be greater than that of the cold stream, which means that we have to split C3. One possibility is to do an even split like I've shown it here, which we've done and eliminated C3. Wonderful. We proceed with the design. Now we've taken care of C4. We're getting very excited and very happy. Now we have C1, which we can partially deal with this way. Unfortunately, now we have a problem, because now we've generated a situation where the feed stream feeding this heat exchanger at 156 is trying to cool a hot stream, which leaves the heat exchanger at 550 kilowatts at 165.6. And you see here the difference between these two temperatures is less than 10 degrees. What that means is that this temperature around 65.6 is too low. It has to be higher. In order for it to be higher, the heat duty of this heat exchanger here, this one that I'm indicating, do you guys see my mouse? Do you see my mouse? Somebody say yes. Wonderful. Yes. So this duty has to be lower, which means I have to do a different split here, which means we have to backtrack and do the split some other way, right? The idea being that we distribute the heat transfer such that the temperature of leaving this heat exchanger in H2 is higher, which we did. We can proceed with exactly the same steps that we did before. And now we have a situation where 156.6 meets 175. Sally meets Harry with more than 10 degrees. Wonderful. We can now position our last heat exchanger and then trim. Why is it important that students go through this design in a systematic way in class time with the lecturer? Because this kind of problem is going to come up in their designs, it's going to come up in their exams, and they have to know how to get out of trouble. This has to be done in class with the students. This is one example why I flip, because if I was to spend all my time in class transmitting information and not working with the students, I don't get to do this with them, and that's their loss, and it makes them less efficient engineers and designers. The last thing that we do in the second week is to deal with threshold problems, basically problems where there is only heating or only cooling, not both. I'm not going to go into more detail about that. The last week is on basically heat and power integration per se. Basically, we teach the students to extract process data from a flowsheet simulator for hand synthesis, how to use the grand composite curve for optimal selection of utilities, and how to optimally place reactors, distillation columns, heat engines, and heat pumps within a system of process streams to minimize the usage of utilities. So basically, the idea of safe side approximation is you take the real process streams with, let's face it, they are not constant values of flowing heat capacity. We approximate them by piecewise linear segments. Safe side means that all the hot streams are approximated on a temperature enthalpy diagram from below, and all the cold streams are approximated from above. Okay, that means that we are underestimating the available driving force, which is fine for safe side approximation. So we teach the students how to do this from real flow sheet data. Grand composite curve, well, the idea is nothing really specially new. Basically, we actually had the data for grand composite curves once we do targeting. Basically, all we're doing here is plotting the residuals on the x-axis against temperature intervals on the y-axis. That information we already had. So, for example, for this very simple system involving 2 hot and 2 cold streams, we have a hot target of 2,360 and a cold target of 1,860 with a pinch temperature at 150 degrees centigrade on the cold side. Now, we could implement this design with just one heat utility, anything above 220 degrees centigrade, and one cold utility, anything under about 30 degrees centigrade. Or we could instead use multiple utilities and thus save money, because intermediate pressure steam is cheaper than high pressure steam, and definitely boiler feed water is cheaper than cooling water, because boiler feed water generates energy as opposed to cooling water that just removes it. Okay, so we could use this to marshal our energy targets by utility type. Advantage, obviously saving money. Disadvantage, to actually implement a design for the grand composite curve I showed before, we now have to deal with 3 pinches, not one. There's the process pinch, which is this one here, but we also have a pinch because of the intermediate pressure steam, and another pinch because of the boiler feed water. In fact, these pinches are this one, and this one. It makes the design more complicated, but it is worth considering because we significantly reduce the cost of energy. Regarding the positioning of reactors, reactors, distillation columns, heat pumps, and heat engines, very, very briefly, exothermic reactors are, of course, heat sources. Therefore, they should be placed entirely above the pinch. Endothermic reactors are heat sinks. Therefore, they should be placed below the pinch. Distillation columns have to be positioned either above or either below the pinch, not across the pinch. Very easily explained using the grand composite curve. Here is an example of a well-placed distillation column entirely above the pinch. Here's the pinch. But if we decide to place it across the pinch, basically what we're doing is we're not heat integrating the distillation column. Its reboiler and condenser duties are added on to the targets we had before. So that's a clear reason for opting for this solution and not this one. And what's nice about the grand composite curve is it allows one to integrate rather complex distillation column systems within an existing process very nicely. Heat engines have either got to be positioned above or below, not across, and heat pumps have to be placed across the pinch, of course. A quick summary of what's covered in those 3 weeks. Again, first week, very simple introduction to hand synthesis, keeping it really simple for the first week. We start the students walking, not running. They have to understand what the pinch actually means and how to use the concept of the pinch for very simple designs, how to target and how to do simple basic hand design, nothing fancy. Second week, more advanced topics, the idea of heat loops, the idea of minimum number of units, the concept of stream splitting, how that improves the capability of designing from there, and the idea of how to deal with threshold problems, which are basically pinch problems with only 1/2 of the problem actually designed for. In the last of the 3 weeks, how to make real these tools that we've acquired, how to extract data from flow sheets, how to use the grand composite curve efficiently, and how to position reactors, distillation columns, heat engines, and heat pumps within a process. That covers what one can do in about 3 weeks of lecture material and associated exercises. And with that, I complete my coverage of Henn synthesis. Over to you, Warren.
Okay, thank you, Danny. All right, let me share the screen. Okay, now what do I have here that I don't want? What I have to have is this over here. Okay, everyone. Well, I hope you're ready for this. Equipment design and costing, capital cost estimation, profitability analysis. Those obviously are key subjects throughout design. Okay, and I'd like to offer some guidance.
Warren, if you don't mind my disturbing you,
Yes,
can
go
we
ahead.
keep it a
please.
little bit shorter so we can recover some time? We are running a little bit late.
I'm aware of that, Rafi. I will do my best. Okay. All right. So you need to, consider teaching equipment design after you've synthesized the process flow sheet. Okay, so do you need to teach heat exchanger design? Well, it depends upon the quality of your heat transfer course. They should have covered shell and tube heat exchangers. Okay, we do that in chapter 10 and chapter 12. Separation tower design. Well, again, it depends on the separation course. In my view, the students should be well aware of the importance of estimating the column diameter. They have to be aware of using what's involved in calculating the flooding velocities. Okay, we do that in our chapter 13. Okay, I'm going to skip for this. It's having to do with pumps and compressor expanders and also chemical reactor design. Okay, now I'd like to go to capital cost estimation. Okay, so we're recommending that begin with the estimation of the equipment purchase costs as a function of equipment sizes using graphs and simple equations, and show estimation of installation, what are known as bare module costs, and move to estimation of total capital investment. So I'll try to guide you through this quickly. I think most people are familiar with it. Okay, so if we look at our figure 1610, chapter 16, here's for a shell and tube heat exchanger. And this is the base case. This is where you have a carbon steel exchanger. The pressures are low, less than 100 psig. The tube lengths are 20 feet long. Okay, so the purchase cost is a function of the size factor, which is the area. Hopefully everybody here knows this. You have different kinds of exchangers, and the curves then go like that. These are log curves. If you look at the base cost as a function of the area, the relationship is this for a floating head exchanger, fixed head exchanger. Once you have got the cost of the base cost computed, then you want to make corrections. If the pressure is greater than 100 psia, we have an equation like this that gives us the pressure factor. If the materials are different than carbon steel, we have then a materials factor. If the tube length is different than 20 feet, well, then we have a materials factor, and you multiply by those factors. I'll skip through this. Now, in the book, we spend a lot of time talking about what is involved in going from the purchase cost to the installation cost. And I won't take the time to do that now. In effect, we come up with a factor. It's called the bare module factor. If you take the purchase cost and multiply by the bare module factor, you have the cost of purchasing the equipment plus the cost of installation. This is so important. So, this is for different kinds of vessels here, the vertical pressure vessels, the columns, all right, and for compressors and drivers and sensors, so on. Separate bare module factor for each. Okay, now the students very badly need to understand this, in my opinion. Okay, here's the battery limits. That's where all of their equipment in their process is sitting, in the battery limits. You got storage vessels, okay, you're at the railroad tracks or the river or whatever, and you have now tanks, okay, where the feed chemicals are stored. Those go into the process. Coming out of the process will be, product chemicals. Those will go into the storage tanks and they'll go off for shipping, okay? Now, all processes will require utilities. So the students need to know about the utilities, all the different kinds of utilities. You can read this. I don't think I have to tell you. You need to be able to take waste streams and treat them. So we have to have a way of charging ourselves for that. And you need to have a way of disposing the solids and charging yourself for solids disposal. Oh, yes, you do need canteen and maintenance shops for the engineers and the operators. And you need services for engineering, laboratory, library, R&D, office, and you need sales and shipping. All right, all of this is part of now what you have to include in your total capital investment. Okay, now, to me, for my students, this is very important. I think I'll take very little time for you. I think most of you all know this. You need to be able to sum up the installation cost for each kind. So you have the fabricated equipment, that's anything that doesn't have a moving part, like towers, for example, okay? And you sum those all up. You have now the installation cost for the process machinery. That would be pumps and turbines and things of that sort, anything that has movement, okay? You got spares you got to include. You have storage vessels you have to include. You have the cost of catalysts that you have to include, and you may have computers and things like that. You add all those things together and you get the total bare module cost. And then you need to go and estimate the cost of preparing the site for your plant. Well, 10 to 20% of the total bare module cost is typically what's used. And then you need to be in a position for the service facilities. Well, 5% of that would be used. I'll skip this, I don't have time. Okay, and now you get the total permanent investment, CDPI. And you then take 8% of that to get the cost of contingencies and contractor fees. You're in the early stages of design, you put it away an extra 18%. Okay, and that gives you the direct permanent investment. I'm sorry, what did I say? There's the 18%, my mistake. And that gives you now the total depreciable capital. That's what I should have said. And now you have to estimate the cost of land and the cost of startup. And all right, we use these. We take a multiple of the total depreciable capital for them. Okay, that gives us a total permanent investment. Then once you know the operating costs, you can then estimate the cost of working capital and you get the total capital investment. This is a very important part of our chapter 16 and it's discussed at length. Okay, now, having done that, we ask the students to solve a homework exercise. We say, here's a distillation complex. It's got the tower, it has the condenser, it has the reflux accumulator, a reflux pump, okay, the reboiler, a reboiler pump. There are 6 items they have to estimate. So we ask them to do that, and I won't go into detail at all about that, okay? One thing that we do is throughout our chapter 16, we have the equations that are needed to estimate the cost of each of these. Okay, well, fortunately, Professor Russell Dunn at Vanderbilt took all of the equations that we had and he programmed them in a spreadsheet, and that's available and it's discussed in section 16.7. The students use this very actively. Okay, also, when you are running Aspen simulations, there is something called the Aspen Process Economic Analyzer, APEA. You just simply ask it, okay, to estimate the purchase and installation costs. And it will just do it straight out, okay? We give instruction in section 16.8 as to how to use the APEA. Wanted to mention that. Okay, now for economics and profitability analysis, let me look at timing that now. Okay, 57, where am I? Just a second, looking fairly good. All right. Okay, in this section, we want to focus on the issues associated with time value of money and approximate and rigorous profitability measures. Okay, these are very important for the students when they're going to do their design projects in the next semester. Okay, the students need to be able to, appropriately estimate the relative value and cost of proposed long-term investments or projects. And the time value of money becomes very important. So I think everyone around here knows what we mean by the interest rate. And I'll just simply skip past this. And we talk about how you can compare, okay, two pieces of equipment, each having an initial cost, different initial cost, each needing a certain amount of money for end of year maintenance. Each one has a different equipment life. And we talk about how do you compare these? And we use present worth and capitalized cost method. That's a standard thing. Now, very important is when we're doing the profitability analysis, we do it approximately at first. We estimate in the third year of production, the annual costs, the annual earnings, I should say. Okay. And, okay, how do we get that? Well, the pre-tax annual earnings is the sales, what you get in the way of sales minus your cost of sales. All right. And we discuss how to get the cost of sales in the lengthy table 17.1. Okay. Now, usually we use after tax. So we have to take the pre-tax amount and multiply it by a tax rate and subtract that. Okay. And then we divide through by the total capital investment. Okay, that's the total permanent investment I just discussed and the working capital. This is the standard return on investment, ROI. Okay, other things that we discuss with the students, very important things, have to do with, just how when you're estimating the cost of operating in the first year, the second year, third year, what we do is we say, okay, you design the plan for 100% capacity, but you take 90% capacity. And in the first year, only a half of that, because it's going to take you a while to get to the point where you can get to 90% of capacity. You finally get to it in the third year. Okay, I'm going to skip past this. These things are needed. Then when we go to the rigorous profitability measures, we have to be concerned with cash flows every year in the construction years and in the production years. Again, I'm going to skip over that. And we have to know how to depreciate. In the United States, it's the modified accelerated cost recovery depreciation. And we have a 5-year schedule, 7, 10, and 15 years. Most everybody uses 5 years. We teach the students how to do that. Then we take an example, a complete example, which, we discuss. It's example 17.29 in the book, and it just shows them over a 15-year life of a project, okay? It shows them how to how in every year, how you compute the so-called cash flow. And then what you do is you take the cash flow and you discount it to present value. All right, that's in the same value here. And your cumulative present value is just that 30 million. Okay, now, all right, for the second year, it was 30 million, but you discount it back a year at 15% interest rate. and now these two get added together. Well, this shows them how to now take the cash flow for every year and simply discount it back and get the cumulative present value. Okay, this is a very important measure. This is called the net present value. And we then teach them, if you set the net present value equal to 0, what would the interest rate be? That's a very important that we call that the investor's rate of return. So I'm skipping over that now with you. And a very important part of what we do for our students is we discuss in the book, in chapter 17 at the end, 17.8, I believe, the profitability analysis spreadsheet that was designed by one of our former undergraduate students. And this will estimate the approximate and rigorous profitability for a potential chemical process and or product design. So that's it. That's all I have to say for that. So now I'm going to stop the share and I'm going to turn it back to Danny.
So Danny, in the interest of time, can you just briefly say the importance of plant-wide control, and then we can take the questions. You're muted.
Yeah, actually, I am reading my chat, so I know what you want me to do. I'm going to give a very, very brief description of materials that we teach in the 10th and 11th week of the capstone design course. Basically, it covers process control considerations for individual units and complete processes, as well as teaching students to draw process and instrumentation diagrams. I will give you a very short overview of what is covered at the Technion in 4 hours of online lessons, 4 hours of class meetings with students, and 6 hours of active tutorials. Much, but not all of the materials that we teach in this part of the course are taken from chapter 20. So the learning objectives are quite straightforward. On completing this part of the course, the students should be able to explain why control issues need to be handled as part of the process design. They should be able to apply qualitative controller configuration rules to suggest controller configurations for individual units, to be able to accurately draw a PNID, and to be able to apply the plant-wide control system design method of Lewin and co-workers to reliably design plant-wide control systems. And basically, this allows the organization of the control system design so that the objectives, the controller objectives, are achieved in order of importance. So in summary, this is what we do in 2 weeks. Why is control important in process design? Basically, if we are not able to control our process, there's no point in doing the design. In order to ensure that our design is appropriate, we need to be able to show that we can control what we design. This may require the addition of more degrees of freedom, bypasses on heat exchangers, for example, which will change everything in the design. So therefore, that has to be done in advance. In my plant design course, which is the extension of the capstone course, the first task that I give my students is to design a complete control system before they do any design at all, any detailed design at all. This involves controlling individual unit operations and also learning to use the piping instrumentation diagram, which that's a P and ID, not an ID. There's a P missing. In the second week of the 2-week segment, basically we cover the Lewin approach to conceptual control system design for complete processes. That's a very, very short summary. I prepared obviously more material, but we are really running out of time. So with that, I will close my discussion on control system design and how it is included in the design course. Thanks.
So thank you very much, Danny and Warren. Before Iqbal starts with the discussion on the third part, and he will take the questions that are still in our system, I just want to remind all the participants that you will now receive the poll for this webinar. There are 8 questions. Please answer the poll, so it will be useful for us. And then Iqbal will start, and I will give Iqbal about 10 to 15 minutes. And then after that, Edwin will start. And we can continue as long as Edwin and all of you are interested. I know that Edwin has to attend to a birthday party also.
just for the record, right now there are 66 participants. I'm going to keep looking at that window now, see how many people.
Yes.
But
Yes,
but
so
as
we
far
have
as
to
I'm
also
concerned,
think
I
that
haven't-
people should not leave. Okay. Iqbal, please.
Good afternoon or good morning, everyone. And thanks, Danny and Warren, for very useful insight in heat and power integration, and as well as costing and control. I can see a number of questions on the chat box that I'll maybe pick few of them. The one we left with from Sheshagiri Rao, where the question was whether a specific design course is required for a Bachelor of Petroleum Engineering program. I think this question is relevant to us at Bradford as well, as we are planning to embark on new petroleum engineering program. So to the panel.
I'm not sure that I understand the question. I'm not sure that I understand the question.
So for example, Danny, if we would like to introduce a course in Bachelor's in Petroleum Engineering, will the similar process design or design project will do, or do we need a separate or a more specific process design course or design project?
My take is that unless you're talking about petroleum extraction, which would require additional segments to be added, if you're talking about processing, it's all in. And I think the way to make it real and relevant to your course would be to make the design project relevant to your course. Okay. You have to use a process simulator that can handle modeling of crude oils for as long as we'll have crude oil to process, of course. But okay.
Sure.
Yeah, but I mean, I think they all do that. I know Unisim has that capability. I'm absolutely certain that Aspen also has this capability. So there's no problem giving students a petroleum-based project to work on, and that's what will make the course real for them, because they're working on an absolutely relevant project. That's my take. Maybe Warren has other.
No, I agree with that, Danny.
Thank you. I've got a question on engineering ethics, which you can see on the chat box, but you may want to respond in writing. So I'm not going to go into that. I'll move on to the next question from Dr. Juarez Romero. It is about whether we should have one design project for the whole class, or separate or multiple design projects. I can share with you our experience in few UK universities. For example, at Bradford, we have got multiple design projects, about 8 to 10 for a class size of 70 to 80. While I know that Hull University, they have got one single project for all of their students. Is there any view on that?
Warren, you answer first.
Well, you know, I have spent at the University of Pennsylvania for the last 75 years, has had separate projects for groups of 3 students. And, you know, I've been at Penn now for 54 years. So this clearly is an approach that I understand and appreciate. In the early days, we could do that because we had so much chemical industry up and down the Delaware River in the Philadelphia area. So the people from the companies would come and they would consult with our students as they were working on the problems and give them advice. Okay. As years have gone by, though, we now have the Zoom communications. It doesn't really matter where they are. And so it is now possible to get a group of consultants together from all over the world. And we do have them from Beijing, they call in at 4 in the morning at Beijing time to work with a design group at 4 in the afternoon at Penn. You can do that. So I think it does make it possible now to have multiple design projects. Okay, much more easy to have multiple design projects in a course.
Thank you. Thank you.
And I'd like just to add one comment. So long as there is one faculty member per project that is assigned to make sure that there is a reasonable grading across the projects. if all the students are working on different projects, there has to be some common basis to give students grades.
Okay, we
In-
have
at
the
the-
the following, Danny. We
Yeah,
have
yeah,
an
yeah.
adjunct professor.
Yeah,
one
no,
of
no,
our
no, Warren,
former
you
students.
already explained the system, but not every university has the luxury of, harnessing the entire faculty in favor of such a venture. At the Technion, we do not have this luxury, and I think that if you have one teacher handling the entire class of between 50 and 100 students, it is not practical to give individual projects. It's just going to be totally beyond the capability of one faculty member to reasonably grade reliably all these projects. That is the reason why we do things differently, and I guess that will be the difference between Bradford and Hull, right, Iqbal? I'm sure in Bradford, I'm sure you're not on your own with this, right? You have a number of faculty members.
Yes, at Bradford, our take is that all members in the core chemical engineering team has to supervise a design project. While at Hull, you are right, there's only one or two colleagues who actually take care of.
Here,
can I make
here I will add one of my experiences when I was teaching. So 1 year, despite the objections of the teaching assistants, I said we will allow the students to choose their projects themselves. And there were 20 groups, and they all chose their different projects. And these were all very, very fancy things that they would like to make. And then once I introduced them to the simulators and the chemicals that are found in the simulators, they came quietly to me and said, "Can we change our project?" Because once they found out what to do with the chemicals that are not in the simulator and all the extra work that they have to do and the models of the unit operations that are not there, they all changed to the same old commodity chemicals to make.
Thank you for the contribution. Let us move to the next one, which came from Denmark, Said Mansouri. Said, if you are around, can you please just explain your question? I think I did not get it quite right. Said, are you there? Right. Okay, so the question is how would be setting in combined programs where, for example, students take part of their education with the industry? Maybe we can leave it in case Sahel comes back.
I can. Okay.
Yeah, go on.
No, but my experience in this is very limited because very few of our students are working with industry in a way that would make them capable of taking on a design project of the scale that we require in our faculty. In principle, there's no problem with that. Again, once you start allowing students to do different projects, you have to make sure that you have staff available to support them reasonably, and that's going to be the bottleneck. I think not so much what students are capable of doing or not, but whether you have the people in place to manage such a project, such sets of projects. Warren's university is handling this extremely well over a long period of time, but that's because that's the way things work there. It doesn't work that way in every place. It's more complicated.
Maybe a side comment to add there to what Danny was saying. The one thing is the ability to provide quality advice to the students. The other one is to have consistent and grading and assessment of the work, which is important from an accreditation standpoint, but also in terms of fairness and equity for the all the students involved. You don't want, for example, one of the things that can happen is from an academic standpoint, we may focus more on plant-wide design or large level integration, whereas an industrial engineer may focus very, very specifically on a little bitty detail in the PNID that we may not think is as academically interesting or what we intended for the course outcome. So there's an issue of fairness and equity across those things. And as Danny said, having enough bandwidth to provide the students the right support. So.
A quick thing, we have an adjunct professor who is in close contact with all of the people in the local industry that advise our students. They suggest the design projects. He looks them over carefully and essentially offers them as to the students to choose a project. Okay. We schedule in such a way that he can attend many of the design meetings. And in the end, after the advisor has had a chance to read the report that they write, this adjunct professor reads every one of them, and he is the first one to assign a grade, and then asks the professor who did the advising if the professor agrees. So that's the way we do that.
Thank you for the contributions from the speakers and the panel members. Right, so the last question, I think, which I will ask to the panel members, and I can share my own experience as well in that, came from Sheffield University Mozambique. How individual student contribution is assessed in group projects, particularly in case of online projects. So you may have a group component in your design project, and students are assigned to it, and how do you assess? What are the practices? I mean, I can share my Bradford experience later on.
That is really a tough question. In the capstone design course at the Technion, all the students get the same grade. It is their responsibility to pull weight. It happens very often that there will be some students who do not pull their weight. How do we know this? If we look at the grades of the projects plotted against the grade in the final exam, typically every project grade will have a spectrum, almost the entire range of possible exam grades. In fact, there is almost no correlation between the exam grades and the project grades. That's an unfortunate result, but the bookkeeping and the support needed to make any change in this is a problem. In the plant design course, I'm a little bit smarter. First of all, a percentage of the grade is awarded by the students themselves. That can work partially, although our students are very, very unlikely to give low grades even for non-performers, but you do see this. At least there's some variation. Those are internal checks within the group. To do anything else will require a lot of work from the point of view of the course staff. It would mean repeated interviews of the entire group, some kind of oral exam. It's just the headache involved. We used to do this. The headache involved in this is very, very large, especially if you have a large number of students. But it is a problem for sure. One way to resolve this problem in some way is that if a student fails the exam, his exam grade is his course grade. Therefore, the project grade will not count unless he passes the exam. At least he has to know enough to pass the exam. This is generally an accepted thing in all our faculty courses, and of course, I'm very happy to use this ruling as well.
Thank you.
Can we shift to Edwin now? So I can see Mario has a point. So you can give Mario, and then Edwin can take over if you don't mind, Iqbal.
Yeah, sure. I mean, Mario is to you, but before you speak, just I briefly share our experience at Bradford. We use digital peer review platform where the students peer review each other, and we have got a factor which we use to actually adjust the group project mark or assign individual the group.
I was just going to add, we do something similar. Even though I don't teach design anymore, I am involved because it's something I'm passionate about. We use a combination of a digital tool that was developed at Purdue called CatMe, which is a survey tool that they developed for doing internal assessment of teams, where the students doing a self-assessment of their contribution along with the other team members' contributions. And whenever there's discrepancy, it provides an opportunity for the instructor to have a discussion with the team. So that's proven very helpful. Another thing that we do is on every report for the capstone class, the students will write out what areas of the report they were responsible for. And very quickly, once you've taught the class once or twice, you realize and you inform the students that it's not a number of having an equal number of bullets, because we know that, you know, you could have one bullet that said, I did all the simulation. That may be a massive contribution compared to having been the one to write the abstract, do the proofreading, format the graphs, and so on. And so when you hold those two things up together, it provides an opportunity to have discrepancy in the grades for a team, because you can point out that a certain, like Danny said, a certain portion of the grade comes from a level of contribution and equity there. So the CATME survey has worked really well for us for at least the last 10 years. And it's not that expensive. I think you pay it's like $150 or $200 for the year, and it covers all students, and it can be used across the curriculum. It's not tied to a single class. So that is certainly something I would recommend. That's been working really well.
Thank you, Mario. Thank you for the contribution. Thank you. I'll hand over to Edwin now for the final session. Edwin, to you. Thank you.
Thank you, Iqbal. Yes, yeah, I think in this seminar we were covering the Americas up to the Asia. So maybe it should be good morning, good afternoon, good evening to all of you still remain. I have considered myself as the official scribe of today's seminar. So Prof Iqbal was saying, you know, I have other obligations, but no, I prepared monologue of 45 additional minutes. No, I will keep very shortly in the summary, and also to put some of my personal notes in there. So you have been viewing in the last 3 hours a seminar organized by PSE for Speed with two main speakers, Warren Saiter and Daniel Lewin. And we had, of course, this panel, of which I'm also a part, Mario Eden, Iqbal Mujtaba, Song Loon. And they were upfront asked a couple of questions. So to give also an impression of who we were facing today, I think we were having on average 80 to 95 participants in this meeting. Around 70% is actually involved in teaching, lecturing. Around 25% is in the role of students, and more or less 10% on the industry side. I noted here that actually not so many questions were asked from the student side in this workshop. So there is still some opportunity to post questions, especially for students, I would suggest. And you all apparently were here to learn, to listen, and to participate in this event. So let's see what can happen with the participation. Now, we were listening to 3 parts. The first part was a general overview in process design courses. We viewed the general structure of process design at Penn and at Technion to a certain extent. I think they were following, of course, the famous textbook. It's for me very special to see the 3 authors of the famous textbook here present today. There are in total, I think, 5. But and these lectures, they include the lectures. I mean, they included also a lot of multimedia and flipped learning concepts in the lecture. And they were describing the balance between traditional and new approaches with challenging case studies for the students. I noted, for example, the development of a COVID vaccine or carbon capture and then carbon into CO2 related to the current world challenges. And the traditional approach is, of course, typically designed for batch or continuous to define inputs, outputs, to do the conversion design, the separation design, the recycles design, the heat integration, economic analysis, safety and risk, plant-wide control, but also life cycle assessment and the use of heuristics were mentioned multiple times to limit the number of alternative designs. Daniel Lewin also mentioned something about that future teaching goes beyond the country borders, and he was involved in a course that was actually split between Israel and China, and that people communicate and form teams via internet. We also learned about the intertwine between product and process design. For example, what to make and how to make it, starting from the chemical supply chain. That not only the product specifications are important or the composition, but also the functionality of the product. Then after this first block, a couple of questions and discussion followed very shortly. Typical outline of a course, the size, the duration, the breakdown, the prerequisites, how to track progress and motivation, how to assess students, what is the role of LCA and sustainability actually within a course, what is the aspect of ethics in relation to geographic location, for example, was mentioned. And I took from this part as kind of a one-liner. Future education is not so much towards books, but much more in the direction of new resources, for example, the internet. Then a second topic followed, that was simulation for process creation. And I think that process simulation here takes a leading role in the design process by calculation of mass energy balance, liquid sizing and costing. There was mention of different softwares. I think one of the last questions was also about what kind of software you might use. It's not always Aspen Plus. There can be SuperPro Designer or Honeywell's Unisim. The basic features in the course in relation to process simulation are also to understand what is the degrees of freedom concept, how to set up design specs, how to perform sensitivity analysis, how solvers work, tier variables and tier streams. And a short demonstration followed from Warren's side on in a multimedia environment on how to set up a process simulation in Aspen. There was a very short, maybe too short note on the aspect of batch process design and scheduling. I think it's important to understand how simulation packages can be used to sequence separations, especially distillation columns, how to estimate physical properties, thermodynamics, and then a discussion followed from Daniel's side on isotropic and zeotropic separation sequencing, how to use residue curve maps and ternary diagrams to identify regions of suitable distillation processes. Last item tackled in this second topic was the second law analysis, where material and energy streams are valued as a function of the work that is available. Here also a discussion was led by Sang Noon on especially the heuristics for new technologies, for example, electrolyzers. And there was a question on how using benchmark processes available from patents already. So how to use something existing to come up with new designs. For here, I took as a key message or a takeaway is that other disciplines, such as nanotechnology, might come in very handy when understanding and designing new processes, for example, vaccine manufacture. And then the last topic that was really accelerated because we ran out of time. I think we're running out of time also now, so I will speed up. Is a short outline on how to design efficient heat exchanger networks, doing heat integration by mapping source and sink temperatures, the basic idea of the temperature interval method, pinch analysis, and the threshold problems. Then there was a very brief announcement on how to do the economics, capital cost estimation, profitability analysis, the time value of money. And then in 2 slides, the aspect of plant-wide control, which I think is a cornerstone because we are dealing more and more with, say, variability in feedstock, biomass, but also think renewable energy. Where control maybe we should flip. If you talk about flip teaching, start next time with plant-wide control. For the economics, I took a takeaway. It will take more than pressing a button to get accurate economic estimates for your design. So my personal closing remark here is that we just witnessed a very complete, but also very classical way of conceptual process design focused on traditional chemical industry. And besides all concepts and tools that we have at hand right now, we might still wonder what new different requirements are needed when we think of new feedstock and products, more complex, think of biomass food or volatile availability of the energy. How the decision-making changes when the processes should be fully circular, maybe not so much touched. And is the product design paradigm also the product design paradigm? Is that the task for the chemical engineer? Or for maybe business developers, I don't know. And then the last one, what are the consequences of a crisis like a virus or a war in the Ukraine right now on the economic analysis in the process design? Because then suddenly feedstocks and products, availability and prices, they change a lot. And this is something that we typically don't think of. So that's in a nutshell how I have perceived this meeting today. It was very nice. And if there are any questions remaining, I'm not sure, I cannot see.
Edwin, maybe I can help you with the questions. First of all, thank you very much with the overview. I see that Joan Cordiner also wants to give an industrial view, and she's still joined. So Joan, if you want to actually give your comments rather than me reading it out, please go ahead.
Hi there. Can you hear me okay?
Yes.
Yes.
Hi. So I'm an academic now, but I was for a long time an industrialist, and I helped at various universities around the world with design projects, and as did my teams laterally in my career. And quite a few universities gave a little handbook or some guidance for the industrialists, and I found that really helpful, because when you're coming in from outside, you can read the course notes, you can read the synopsis of what's been covered, but it's really helpful to have some guidance about, if you're going to use an industrialist, what you want them to do and what you don't want them to do. And I think that what you don't want is equally important, and make sure they understand the rubric. I think the first time I saw a really good rubric was Mario Eden's design project way back in 1990. So I don't think I'd seen one before that, but that really helps the industrialist as well. So NC State, where my daughter went, they had 35 design projects to choose from. And the students got to vote for 5 in order of preference. And they then got allocated, and I don't think they filled all 35. I don't know how many they did. And they had regular meetings with the external person. But I think one of the things that made the grading easier is instead of it all being one report at the end, it was 3 hand-ins. And so it made it easier. And because there was a standard structure about these hand-ins, even though the processes were very different, I think it made it easier from the marking, from what I could see. Obviously, I heard about it from the student perspective, being it was my daughter, but then I spoke to Lisa Bullard, who leads the course there, and she has a book as well about teaching STEM that advocates the flip classroom. But are we marking the design process, the thought, or the outputs? And if actually what you get them to elucidate in their sections of the report, the process they've used and the thinking they've used, it's easier to mark, because the outputs in a sense don't matter. I mean, they do, but it's really, have they actually learned the material? So I thought that was an interesting way of marking. But overall, if you're going to use industrialists, you need to teach them too, and I think that helps.
Okay. Before you answer, maybe there is a question that I'm sure Warren would like very much. It's from Jaime David. If you want to ask your question, please unmute him. You can ask it. Jaime David. Okay. Can you find the team JAIME David Ponce? Okay, I think, let me read the question. When you use the second law analysis, what type of exergy is most relevant, physical or chemical? For Warren.
Well, I'm not familiar with working with the chemical. We've worked with the physical all along. Professor Bob Cedar, J.D. Cedar, S-E-A-D-E-R, wrote chapter 10. That would be a good question for him.
Okay. Okay, then I would just ask Danny, Edwin, whatever the others have said. Do you have anything to say?
From my side, not. I think it has also been a long and an intensive event, so we're maybe also getting towards the saturation.
Yes.
From my part, the Jones issues are really super important if the industrial contribution isn't just going to be to grade the projects at the end, but to be involved with the project throughout the entire semester, which I don't do at the Technion. Regarding the grading at the end, I have a very simple grading sheet that involves quite straight and very transparent rubrics that they just have to give their viewpoints for various aspects of the presentation that the students make at the end. That's worked quite well. Actually, it's a variation of a form that is available in our book also. So basically, I'm using that, and that for many years, I mean, 10+ years has been fine. I really liked the input that we got from Mario. I'm going to look into this CAPME program. This might actually be a big help to solve a real problem.
It's
We
worked
use-
well for us.
I can
Yeah,
mention.
There is a question on, could you please identify the scope of the project assigned to the student group?
The one that I give every year is basically a failed project. I mean, it's a feasible project, but it's losing money unacceptably, because I basically have solved the problem given to the students using all the mistakes I have ever seen over 16 years of experience with other projects. So it's a collection of calamities that lead to failed project, basically, and it requires a student to basically redesign the whole thing. Now, Warren mentioned the usage of the spreadsheet that does the calculation of the economics, or let's say what's available with Aspen. We don't use Aspen. What we have done is we take all the equations that are in the book, all the costing equations, and introduce them into spreadsheets within Unisim, which means that students can do their costing on the fly. They make a change in engineering, and if they adjust the spreadsheets accordingly, that immediately adjusts the economic measures of the process. So students get an instant response to any change they make to the process, how it affects the economics, which is very helpful because they know how to drive, in which direction they need to drive the engineering. This is and it's a very good thing for them to be having in front of them always before they make any change.
If there are any students in the participants now, you have the last chance to ask some questions. And in the meanwhile, you're thinking of questions. There are two questions that Danny would like, because I stopped him from talking about control. One question says, when teaching plant-wide control, may you share some experience with dynamic simulation software? And a second question related is, what software you propose your students to use for design control systems?
The scope is beyond scope for a capstone design course to expect students to handle dynamic simulation as well. We do not teach dynamic simulation. Unisim does have that capability, and for advanced projects, I've had students working on dynamics, and it's very exciting what you can do. The average student won't be able to do this, so we don't require it. Would be a very nice thing to have, but I think it's going to overstretch what we're asking for the average student for such a project. Probably a better solution would be to use Aspen, because I think their dynamic simulator is much easier to use than the Unisim one is. Probably more reliable too. I know that Lewin uses it all the time.
I was going to say that Bill Lewin has written books on the subject of how to use it.
Yeah. No, it's definitely doable, but I'm just saying, from the point of view of how loaded the course already is, to add that to everything else, I think would be just too much. That I don't argue about the usefulness of it. Don't get me wrong. I think it would be very nice to have that in, but there's a limit to what you can offer.
Often it's said that control and design are kind of different subjects.
No, they're not.
No, they should be, but practically you're not using dynamics in your course. You just mention it. So it's kind of like put under the umbrella of a process control course. And,
because I have, sure. But how much time you're going to need to do this properly? That's the problem. Yeah.
Okay, I don't see any questions from any students, but before we stop, let us thank the Thai team. The Thai team members, thank you for organizing it very well. I will just say their first names: Orakoch, Nichakon, Jakrapat, Raksina, Sitida. I hope I've mentioned all of you. Thank you very much for organizing it. And let me also, we are also receiving some compliments. So one person has said, thank you for wonderful and informative presentation. Excellent experience attending the webinar.
Fantastic.
And I will read one more, which is near the end. So thank you very much for excellent work. And a more detailed one. Where is it? Thanks a lot for the lectures and organization of this webinar. I very much enjoyed it and learned a lot. This will help us to improve our process design course as well, and so on. Thank you very much for a great webinar. These are all faculty members.
Great.
And it was an excellent webinar. Our last remark for me that remains is, how do we couple the material and practices that is simulation based with hands-on pilot plant? But that's a question. Let's forget that. Thank you very much for enriching seminar and so on. So thank you all for your participation, to Danny and Warren for preparing all the lectures and giving the lectures. My apology for stopping you a little bit at the end. Thank you for Edwin, Iqbal, Mario, and Bamrung for doing the panel discussions. I hope all the participants who are still here, you got something good out of it. We will put the recorded video on our YouTube channel, and we will also look at the questions and look at the discussions and maybe share them with you.
Okay, I would like to add one thing. Okay, I was going to thank all the people that you did, but more importantly, we all want to thank you. It was your concept to do this. You invited us to do it, and it's very much appreciated, Rafi.
Yes, thank you very much for inviting us, Rafi.
Thank you.
Thank you very much.
Definitely. Thank you very much.